Welcome everyone to this week's Bangalore Probability Seminar. This time we have two speakers. The first speaker is Ujjwal Koley, and the next will be both our local speakers. So Ujjwal will be talking about convex integration solutions for stochastic transport equations. It's very relevant these days apparently, though, because next week on One World Probability Seminar also a very similar topic is going to be presented by Martina Panova. So I think we are getting some sort of an introduction to the next week's talk. So, yes,
okay, so thank you, Srikar, for this invitation and opportunity to speak in this probability seminar. So must confess first that I am not a probabilist by any means. So I guess this talk will be a little different from what you actually see in usual days. And my apologies if it is not interesting for you. Okay. So my aim is to actually simplify things. So I have decided to talk about transport equation, but my entire analysis will go for example, stochastic Navier-Stokes equation. But since for Navier-Stokes you have to work with the metrics, and then things are not that straightforward. So I thought that maybe I will give all the results for transport equation, which is very easy to understand. So in particular, I'll talk about non-uniqueness result for this kind of equations, transport equations. And this method will be very specific. I mean, we'll see that how to construct such non-unique solutions. Okay, so let me begin with a very simple transport equation and deterministic setting. And this has this following form. So rho t plus divergence rho is 0. And you initially start with some density, let's say rho naught. And in our setting, we'll always use that the velocity field is incompressible. So in other words, divergence is 0. And everything started with the following result from Deterministic in '89. So this is a famous paper of Deterministic in '89. So whatever I have written it is a stripped down version of their full result, because I don't need the full result. So you just start with 2 exponent p and p tilde from this interval 1 infinity. And you say that you have given a velocity field which has this regularity. So it's L1 in time with values in W1 p tilde. So p tilde, remember, is that one of the exponent I started with. And this is an incompressible flow, so divergence is 0. So if I give you these two p and p tilde and a u like this, then if you start with any density which is in LP, so Deterministic's result states that you have unique solution. So unique distributional solutions, if you are not aware of this, is very simple, is that it's like a weak solution for this equation. And moreover, you'll get rho is in that space, L infinity in time and LP in space. Okay, indeed, you can do better because you can get continuity in time with values in LP, provided you have this constraint 1 by p plus 1 by p tilde should be less than equals 1. Okay, so let me just say a few things about this, because if you're not familiar with this transport equation. So first of all, if you look at the existence problem for this transport equation, that's very simple, right? So you see this equation here. given U, this is a linear PD in rho. So if you think about like the traditional way to prove existence, you regularize this equation, right? So to be more specific, let's say you have a kernel. So I denote rho epsilon by taking this convolution of rho with this function phi. And let's say you have also U epsilon. So that's same. So then idea is to write down the equation for rho epsilon, right? And that we can do because I can write del T of rho epsilon. So remember this is a linear term, so it will go on rho epsilon plus divergence of what I need, rho epsilon U epsilon. But as you know that since there is a non-linearity, so I cannot simply push the rho epsilon U epsilon inside divergence, so I have to subtract it. So basically what you will subtract is this rho epsilon U epsilon minus rho U if you regularize this, rho U epsilon. Right, that's what you get. And the entire work of these deep Lyons essentially is that if you do some manipulation, this right hand side, whatever I have written, this is the commutator essentially. This you can, roughly speaking, you can write like rho epsilon times gradient of U epsilon. Okay, some algebra will give you this. And now we will appreciate why we need this kind of bounds. So there's a reason not strange, because if you think this is like LP, so in order to have a good commutator bound, for example, things to be L1, you require this guy to be also LP prime. So then you get L1, right? The product of LP. And this one is precisely making sure that. So in this region, Sobolev embedding starts to kick in, and W1 P tilde will be in particular in LP prime. So gradient of U will be in LP prime, and this will be in LP, so that the bad sets of these both guys will not merge together, and you don't see the bad sets. So this guy will be in particular in L1, and everything will go. So in particular, what I wanted to say is that existence result is not a big deal because it's a linear equation, and once you have LP bound for rho, that's why we are working on. You can use just weak convergence to pass. So no issues there. So the question here to ask whether we have a unique solution. That's most important. And that's the main contribution as far as I understand what to say. No, so I'll come to that. So this is what I have written because this is the framework I'm going to use for the later part of my talk. But I'll state the general reason. I'll just mention. So yeah.
What is the statement that part is not?
No, so I'll always use divergence.
But since you asked already, so Lyons one can work with divergence U, which is bound.
Okay. So there is no.
But for the specific constants of the talk about, you do need. Okay, and in the class, so there he introduced this normalization.
Yeah,
So that's the discussion. Now, but we have to do the example with this. So, exactly opposite situation.
Mainly, what happens if I move away from this region where P and P tilde does not satisfy this? Do we have uniqueness, or do we expect non-uniqueness? So that's our question of what happens here. But in general, even for the deterministic case, it is still open. It's not known. And instead, we look at this condition because, as I told you, that just to make sense of this weak solution, I need the product of rho and U to be in L1, right? And in this region, so this is, you see, this is little further than 1, right? So in this region, you don't see the Sokolov embedding. So that means W1 P tilde will not give you bound in LP tilde. So I'm interested in this region because in this region, Sokolov embedding doesn't work. So there's a hope for non-unique solution. But then I have to be careful when I'm defining which solution because I have to make sense of this code. Right? So you cannot just use rho to be LP and U to be LP. So rho U will not make sense. Okay. So additionally, I have to assume that U also has LP prime, so that this makes sense. Anyway, so this kind of non-uniqueness result has been worked by many people. Started with the work of Oscillatory and Stefano Modena, and then there has been some improved version of that. And this Seti also worked with these two people. And if you work, so these are like sign changing solutions. So rho can change sign. So I'll be giving more details, but just to differentiate these two types of results, here rho can change sign, but here you can say that rho is non-negative. That's the recent work by Berlins and the difference between these two results is that the way you construct solutions, so that can be very different. Okay, so today I'll only speak about this, but you can modify this result to get this in a non-trivial way, but still that is possible. So I'll simplify things and just talk about this way.
So in classification, isn't to see how density is progressing before
yes, I mean, if you like, so they say there are, anyway, I mean, at the end, this solution, whichever I construct, they're not physical. So I don't know, people think I agree with you that I would prefer that to have non-negativity condition. But people give different motivations. But anyway, these solutions are not physical. Yeah, no, but yeah, because here only uniqueness makes sense, the positive reaction result. I mean, makes sense in the sense that's the difficult part. So that's why we're looking for, so this is an interesting question, that if you go beyond this region, so do you really expect uniqueness, right? And in fact, if you work with non-negative solution, this result is not optimal. You can even go a little far away from one, still you have uniqueness. That's the result.
So the existence goes to plane that works for any PM.
Yes. So for existence, you don't need, for example, W1 P tilde regularity because you just want to make sense of the product. That's all. So if you give me U is in LP prime, I will be happy to do so. So that's not interesting. Okay. So now, yes, please. D is the dimension. No, or means okay. I'm not. So this is open. That's what I said. In general, this problem is open. We don't know, but we can say something in this region. So that's what I mean. Okay, so let me just also state the kind of result they produced in the deterministic setting. So again, you start with this exponent P and P tilde. So in fact, you have to just exclude infinity because in the case of P equals infinity or P tilde is infinity, you go back to classical situation and then you have uniqueness. So you have to exclude it. And what they are saying that you look at this set E, so you start with any smooth, let's say mean zero function, density rho, tilde or rho bar, and smooth divergence free velocity, let's say u bar, and you look at this set. Look at all the points T where they exactly solve the transport equation, right? And this convex integration method will produce solutions, for example, u, velocity in this space. Again, don't be surprised by this because this is where I need to make sense of the problem to define its solution. And this is typical regularity, which is also like Deterministic kind of regularity, and this is also the same. So you get u in this regularity class such that this rho, you also get rho. Rho and u satisfies this equation in the sense of distribution. And rho and u will be exactly same as rho bar and u bar once you are in this set. So if T is from that set, will be. So the claim is that this will give you non-unions. Once you prove such a result, I'm not giving a proof right now. Once you prove such a result, this will give you non-unions. That's very easy to see. Why? Because you in particular choose u bar to be identical. And you choose rho bar to be 0, let's say in this interval, and connect it smoothly with a function of x only, that's important. And not only its function on x, this also has mean 0 in this interval. So that's my choice, rho bar and particular choice. This convex integration is going to give me a solution rho bar u bar which solves this equation at least in this interval, right? Because here it's very easy to see that u bar and rho bar solve this equation. I mean, u bar is identically 0, rho bar is 0 in this interval, and it's independent of t, so time derivative. So I'll get at least solution here, but most interestingly, I will start with 0 data. I mean, rho 0 is 0 because it's here. And rho at final time, I'll get this function. And this will give you non-linearity because for transport equation, if you start with 0, 0 is always a solution. No matter what u is, 0 is always a solution. So the point I wanted to make that this is actually a non-physical solution because you are starting with nothing, you are producing something. So that's very controversial. But here there is a subtle point. It's not really what you think that you are starting with nothing and producing something. As I said, this A has mean 0. So you are somehow hiding the information that you are getting a non-zero. Anyway, let's not debate on this whether these solutions are physical or not non-physical. But mathematically speaking, you can produce such a solution. There you get non-zero. Okay, so I will try to give a proof of this result. Before that, let me say what we are doing. So first of all, I want to mention that you can actually deal with also diffusion. And that's non-trivial because if you think like this, that the nonlinearity is giving you non-uniqueness, but this diffusion will smooth out things, right? So there is a competition between them. But this non-uniqueness is so strong, this non-uniqueness result is that even if you put diffusion, still, I mean, that's not a trivial. It's very non-trivial. It can handle also, but not for free. You have to put extra condition on P prime, right? So if you're, for example, that's very easy to see. If your U is like ellipsis, classical flow, of course you get uniqueness, but you have to restrict the regularity of U in a way that you are below this W1 infinity class. So there's a hope for non-uniqueness and uniqueness. Okay, so the kind of result we put in the stochastic case is that we are more interested in what happens if you put a stochastic noise here, random perturbation. So we tried out 3 different kinds of noise. So one is like additive noise. If you are not familiar, don't bother. It's just G is constant. It's independent of O, right? You think of like a Brownian motion. You can have linear multiplicative noise, so 0 would be like those. Or you can have like transport noise in second interpretation. Anyway, the message is that why one should even care about this stochastic perturbation for various reasons. One of them is that, which is very non-trivial, is that you can extract some regularizing effect. So just to give a simple idea, for example, if you work with classical ODEs, you need your flux to be like ellipses to get a unique solution. But in the stochastic case, if you put a Brownian motion, then you can work with Holder continuous. Regularity still you get. Okay. So in general, one can expect some kind of regularization. Okay, that's the one thing. And second thing is that, like the work of Del L, is whether one can actually improve this relation of critical exponents by using it. And of course, another thing is that you get probabilistically strong solution. So that means I'm giving you a probability space and filtration and all this, you construct this. That's very different from martingale solution. But here you will get probabilistically strong solution. So if you are familiar with this, it's like Skorohod compactness argument you always use, and then you lose the probability. But here that is not the case. This is probabilistically strong. Okay. Sorry. Yeah, please.
If you don't have the Laplace integral,
That's even easier. Because as far as non-uniqueness is concerned, this is the culprit, right? That gives you non-uniqueness. This is bad term in my case because this will smooth out things. Right? That's bad for me as far as non-uniqueness is concerned. So this is much stronger statement, not having Laplace. Well, I mean, that's in a different direction. I agree with you. I mean, we haven't tried many things. In fact, the final result, what I can tell you that we are not successful in capturing this regularizing. So in particular, this noise is not strong enough to give you regularizing effect. So what we are
We are saying that divergence term is the one which is created. So space term is
it's not space, but the nonlinear. But I agree with you. One can try different types of noise to see. Correct. Yeah. Okay, but that effect is here. For example, if you know Stochastic, this will give you like a Laplace. That's there, but still strong, not strong. Okay. So I wanted to give a glimpse of the proof. So, but again, I'm not. Okay, yeah. So I'm not familiar with this. Okay, anyway, so the kind of result we produce is the following. So as I said, we are producing non-unique solutions, which are non-unique in the sense of law and in the appropriate class. But the main thing is that in the stochastic case, you can prove this result at the beginning up to stopping time, TL. And then, of course, there are ways to extend this. Okay, so this is kind of result we get, typical result. So I'll come back to the stochastic case if time permits. Let me first talk about this deterministic one. How do you prove such a result, which I showed just 2 slides back. And this is the main proposition. So main proposition is the following, that you start with any delta, okay? And you start with a solution, not solution of transport equation, but let's say a variant of transport equation, which is smooth in a way. Because as you see that last time what I showed, that if you regularize things, then right-hand side, you expect a term which will be, or not, you can think about that commutator. So I'm starting with this regularized version of transport equation. So my solutions are rho naught, u naught, and r naught. And then this method will produce a solution rho naught, rho 1, u1, r1, which satisfies exactly same equation with this additional bound. So all these bounds are uniform in time. And here, if you see first time, you'll be surprised that why some. So first of all, I want to propagate these norms, that LP norm of rho, LP prime norm of U, and also W1 P tilde norm of U, right? So I keep them in the iteration. And the idea is that this R1, this error term, at each step, I want to minimize this error. Okay, so I start with R1, R0. My aim is that R1 should be much smaller than R0 in some way. And it's not difficult to see what should be appropriate norm, because if my rho naught is in LP, U naught is in LP prime, so R0 will be roughly of same order, right? So that would be A1. So I want my R1 to be much smaller than R0. In particular, I can choose, give you any delta, and then you give me any delta, I can make R1 smaller. And also, if R1 is 0 at some point, so then R0 is 0 at some point, T, then R1 is also 0, and essentially you stop the process. So rho 1 will be 0. Now I have given it for only two steps, that you start with rho 0 and you get rho 1, but you can imagine you can do it for n steps. Right? That's the way it goes. And the main idea is that how do you go from rho 0 to rho 1 so that rho 1 satisfies this, and moreover, it also respects the estimate. That's the main deal. And that's where this convex integration comes, and you add oscillatory perturbations to rho. So there are two ways to do it. So I can give you the exact perturbation, and then I can verify these things holds. Instead, what I will do, I will just unpack the perturbation and show you that how does it work. So let's start with something naive. I need some oscillatory perturbation. So I say that my rho 1 is the previous one, rho 0, plus some perturbation theta. I'm not telling you what theta is. In fact, the game is to understand what theta should be. And I put also theta c, because you know that rho 1 and rho 0 are mean value, having mean value 0. So I cannot guarantee that my perturbation will have mean value 0. So I put a character which will make sure that it has mean value 0. Similarly, for U1 velocity, I start with the previous one and some perturbation, and then I need to put a divergence character because I'm not sure this will have divergence. So now let's calculate what is delta rho1 and divergence rho1. So we have this answer. So we calculate, and I'm not going to write terms which contains theta and w. Instead, I'll focus on these two terms most importantly. You see, there will be a term like theta w, which is coming from rho 1 u1 multiplication, right? This guy will fit this guy. And there will be like linear terms, plenty of them, starting with delta theta and this linear in w and theta. And there will be branch of error terms which contains theta c and w. But these guys are small, so forget about it. Now, as I said, our idea is to cancel the previous error or not. Now, my claim is that this guy, this product of these two will cancel or not. If you think like a Fourier series, you have two highly oscillatory functions, right? And if their product will split, let's say the mean of this product, that will be low frequency object, that will cancel also. So what I'm saying that theta w, this product, partially this guy will cancel or not. And whatever rest will stay, that will be small. That's what we do. Okay. And once you know that how to cancel things, so then you can actually predict what theta and w could be. So first of all, I said it is a high frequency object. So I put a lambda, which is very high for the frequency object. And these are low frequency objects because they depend on the previous level. Don't bother this too much, because if you see that if you take theta w product, these two will precisely give you R0. That's what I want to cancel. So this is not important. what the low frequency is there, right? And I want to construct theta and W, these two high frequency. And that means I should construct this theta j and wj. Remember, this is like a vector R0. I can always expand in the usual basis, right? And for each component, I can cancel. That's what I'm doing here. So I have to tell you what are these fixed objects, theta j and wj. So in the context of Navier-Stokes Euler, these are called Mikado flows. So these are very simple stuff. So I want my theta j and wj to satisfy, first of all, these three things. That there should be solution of the stationary transport equation. So I want divergence of this wj to be 0 and divergence of the product to be 0, right? You remember transport equation? This was transport equation. So stationary solution means this guy drops, right? So I want these two product to be 0. That's basically theta times w. And I want their mean to be 0, but their product to have mean which is non-zero. Okay. And I also want their support to be this. Well, before going into these details, that why do I need them? Let me try to convince you that this is easy to construct. In fact, you can choose any, let's say, cis infinity function which is supported in RT minus 1. And then you just look at this capital theta d and wd like this. So this fixed profile satisfies me. This is more or less trivial because this depends on d minus 1 dimension. And this is easy, so in the df direction. So for example, divergence will be 0. Divergence of product will be 0. It will have mean 0 because I have started with this Q which is mean 0. Product will be just Ej because T square has mean 1, right? And support is disjoint. That's also easy to see because since things are supported in, let's say, d minus 1 dimension, so you can think of like this, right? So I have these functions here. And if you periodize, so this will be like tubes, right? Supported in this interval. So this will be like tubes. And they are in the each direction. So for example, d equals 3, we have tubes in E3 direction, E2 direction, and U1 direction. And you can shift little bit the support so that you still make them disjoint. There are lots of places in R3, so you make it disjoint. Okay, so that's not a difficult part. Okay, so now having constructed such a guy, let's come back to the cancellation of R0. So remember, I'm just writing in each component, so that's why you get sum. And if you make this product of theta and w, you get this, right? You remember that I had some exponent here, this, just to make sure that their product will be nothing but R0. So this is what you get. And the beauty of this, now if divergence hits this guy, so one has to make sure that divergence should not hit the first guys, because then this will speak a lambda, which is not good, right? Lambda is large. But this is not the case because thanks to the fact that this is divergence. So divergence will only hit the slow guy, you will get gradient. And so you are getting like a slow guy times a fast guy whose mean is 0. Correct? It's a product of these two. So now you remember that I need divergence of these to be like divergence of something else. That would be a part of R1. And I want to make sure that this R1 in L1 norm, if I measure, it is small, right? And this is more precisely because you can play the anti-divergence tricks. So this is what you have. In order to find R what, you take anti-divergence of this. I mean, it's very simple if you just forget this. Think like sine lambda x. If you take anti-divergence, you will gain something, right? Because 1 over lambda is 1. This is exactly like this. So you will gain a lambda 1 over order of 1 over lambda, and since lambda is large, you can make it small, as small as you wish. That's how it works. Okay, so that's good, but now you have to do other estimates, right? So like Sobolev estimates, in particular W1 P tilde estimate, right? I pointed out not only you will be happy with R1, but you have to do this estimate, for example. So this is Sobolev estimate I have to do. And let's try to see what would be the Sobolev estimate here. Now there is no way to hide gradient hitting this first line, right? Because your W is, remember, W is nothing but this. If I take a gradient, there is no way I can hide the fact that gradient is hitting the first line. So it will hit, and that will basically destroy all your estimate, because then lambda will pop up in front, and there is no way you can balance these two. You need things to be arbitrarily small, and then you also need things to be small, but in front you got a lambda. So this doesn't work. So we need to modulate our building blocks, and that's why comes the famous idea of Bookmaster and Ricol in the context of Navier-Stokes, where they introduce something called intermittent Mikado flow. So not the normal Mikado flow I explained. You need to bring intermittency into the picture, because turbulence flows typically exhibit this kind of intermittent behavior. Well, now coming from physics, if you put that things into mathematical context, what it says is that your solution, you need to actually concentrate also your Mikado flow. So this is the way you concentrate, right? So you look at psi mu, and I multiply this by mu power a. And the advantage of doing this is that if I now measure any LR norm, so you see this exponents will pop up, right? This is just to change the variable. And also if you take a gradient, and then you know how this correlates. Why I am doing this? Because here I have no other parameters to play with. I want to bring in another parameter, right? So that's the main message. So in short, how are you changing your original Mikado flow? You are actually concentrating, right? This is what. So I have to choose A and B in a way such that I know that divergence of, or rather, the LP norm of theta and LP prime norm of this W, they should be finite, because that's the norm we are propagating. And if you do a little algebra, you'll see that these are the choices.
So lambda is large.
No, mu is also large. So we'll have two parameters. So lambda is oscillation parameter, right? So this is large. Mu is also like concentration parameter. This is also large. So in the end, I have to choose them properly so that I get the result. Okay, so what I want to say that very quickly is that if you do this concentration business, now you calculate your gradient of W. That's what we were calculating, right? And if you do the LP estimate or LP tilde estimate, so that means you get a term like this, gradient is hitting here, lambda is in front. But now I have LP tilde norm of this is given by this. That's because we saw this elementary calculation, right? This is what we're doing. So now you are in business because there are two parameters, lambda and mu. And if you are in this region, remember, this is not what I wanted to prove at the beginning. It was 1 by P plus 1 by P tilde bigger than 1 plus 1 by D. But if I restrict for the time in this one, then you see that this I get an exponent minus gamma, where gamma is positive. So mu can in principle kill lambda. So then you can make this, right? So this is the way you can handle this Sobolev estimate. I am not going to the details of this estimate because the main motivation of concentration is the linear term you can easily balance it. From PD point of view, it's very simple that if you can concentrate one guy, let's say L2, then anything below L2 norm will just very small. So they will balance. Okay, but this is not the end of the story, because now the problem comes here that I need to go for full dimension intermittency. So I want my result to be true for this.
Where did I miss one dimension? -1.
Because Mikados were supported in RT minus. Right. So now if you do a night choice, let's say, you say that, okay, it was like depending on -1 dimension, now I put extra dimension. But then immediately you lose the divergence free condition. This is no longer divergence free. These two, both of them. And idea is that, again, the idea is that you use a very fast oscillation gamma. So I take a function which depends on d-1 coordinates, right? So I'm just giving details for d in the direction d. So I take psi, which is depending on x1, x2 of x d-1, and it has mean 0 and square has mean 1. And I choose my gamma very fast, much faster than lambda. Why? Because in comparison, now if I keep the old guys, they are actually oscillating slowly in comparison to this guy. So I can play my divergence free trick again here. How? For example, if you look at this guy, this is a vector field, right? If you calculate what is divergence of WT, you will see that I will only get some contribution from here. Divergence will hit here, not here, because it is depending on, again, d-1 dimension. So I'll get something like this, right? But now these guys are, although they're oscillating fast, but in comparison to this, they're oscillating much slower. So if I take this anti-divergence trick, which will speak me 1 over gamma, and that will take care of all these bad terms which are present in lambda. Okay, so gamma in particular, I need it to be much, much bigger than lambda. So there is a huge scale of separation. So in terms of Mikado, if you think about the support, previously it was supported just, so after this change of scale, so it will be like 1 over lambda, but now with this 5 new lambdas, I'm concentrating. So by definition, it will be like lambda mu inverse. That would be the diameter of one of these Mikados, right? And I want the size are having supported like this, right? So they will intersect with this ball, and this gamma I need to be much going to infinity much faster than. Okay, so now with this trick you can actually check. I mean, it's not difficult to check that the corrector, whatever I wrote here, this WC, that would be small. So since time is running, I will not go into the details, but once you make sure gamma is pretty fast, then you get it. And but the last but not the least difficult is that now I cannot make theta W if I take the product. I cannot make this to be divergence, and also I cannot play divergence pretty, because this first oscillating guy, now this is square, this cannot have mean 0. So for applying this divergence inverse, you need things to be mean 0, which is not the case. So I cannot do that. And again, the main motivation came from Master and Bicol, where they actually propose that you allow this error to move in time. So I will not be able to prove this is divergence free. Instead, I will allow to move this error in time, and I will cancel that error with the time derivative. Previously, I was not using the time derivative because it was a linear. I can kill by intermittency. But they propose that you actually kill with the time derivative. And once you know what to do, then you can actually do the back calculation. it's not difficult to see that I can calculate what is divergence of theta W. And then I want to come up with Q such that del PQ would be exactly. So this is a vector. Right? Now the drawback is that now you will have another parameter omega, because you are actually transporting the Mikado force. So just to finish this thing, let me just tell you that we have like, so this will be like final building block. This will have 4 parameters, which are lambda, which is oscillation, mu is concentration, and then you get mu, which is, or gamma, which is much faster than lambda and mu. And then you will have a phase speed, omega. Okay. So if you do all the calculation, I mean, it's not the end of the story, because you need to verify now with this new Mikado density additional, everything works. And the message is that it works, provided you are little careful and choose things appropriately, then everything works. Okay, so sorry, all deterministic, yes. So now just 1 minute just to tell us why I said that I could start with Navier-Stokes as well. Because for Navier-Stokes, of course, there are no rho and u, it's only u, and that's a vector. But that case corresponds to our case where p equals p prime equals 2. Okay. So for Navier-Stokes, you iterate LP norm, let's say L2 norm of u. And also gradient, you iterate like W1. Right? So you remember that we had this, right? 1 by p plus 1 by p tilde is bigger than 1 by 1 plus t. So here I'll choose p to be 2, p tilde to be 1, and then you can see that everything works as far as your dimension is bigger than equals 3, which is the physical dimension, and most people are interested. Okay. Because for Navier-Stokes, you just iterate L2 norm, right? C0 in T, L2 in space. And also you iterate C0 in T, W11 in space. So P tilde would be 1, because we are iterating W1. And if you plug in on this, then you see that as long as D is bigger than 3, it works. So this can handle also Navier-Stokes. Okay, so I have how much time? 5 minutes, Srikar? Okay, so I'll quickly say how to deal with stochastic case and why we cannot just use their theory. Well, we need to use them, but we need to modify. So for the additive case, idea is to first segregate the contribution coming from stochastic part and also a random PDE, right? So in other words, if I write rho to be theta plus z, I can actually get equation for z, right? And then whatever is left, I get an equation for theta, but this is a random PD because z is coming here. Z is taking care of the stochastic part. Okay. So idea is that first I truncate. You remember I stated my result for up to some stopping time, and that is coming precisely this, because I need to get uniform in omega estimate for z. So I need to stop my process at some level, and then I apply this deterministic type result so that I get desired solution. That's the way it works. Very roughly speaking. And also for linear multiplicative noise, you use this change of variable. And here you don't need any stopping time because it's much easier. If you do, then you get this equation. Okay. And same thing for the transport noise. If you do this change of variable, you will get equation. Okay. Idea is that you then incorporate this deterministic ideas. So yes, I think this is my final slide. I want to tell why you cannot exactly mimic their approach, deterministic approach. So first of all, remember I said their solution is non-unique because if you start from 0, 0 is always solution. But that's no longer the case for us because of this presence of this guy. So even if you start with 0, 0 will not be a solution, not necessarily be a solution. So we need to devise a different way to prove non-uniqueness, and we decided to break the energy equality. So we have existence of classical solutions, and classical solutions is weak solution which satisfies energy. But the way we are constructing our solution here, that does not satisfy energy. So you have two different solutions. Okay, that's good. And we cannot just iterate the way they did because again, because of the presence of this term Z. So remember, if you remember, they have a result that if your R0 is 0 at some level, you essentially stop the process because then everything will be rho 1 will be rho 0. That's not the case for us again, because of the presence of Z. We need to modify the way we actually propagate these norms. We are again propagating the same kind of norms, but the right hand side, this bound has to be very explicit, right? So here we need to make some difference. Specifically in incorporating the terms which are coming from Z. So these constants means these are functions of time. They are related to the stopping time. Like the stopping time. So basically, this is what I have. You stop your Z up to here so that you have these bounds uniform.
And this is arbitrary.
Right. That's the important. You need to propagate. So technically also there are challenges. For example, I cannot work with R0. For technical reason, I need to modify R0. So I will not be able to give you details why, but for stochastic case, I need to modify. And once you modify, then you see that there is a term like RL minus R0. Right? Modified version of R0 in R0. You need to estimate that guy as well. And for that, I will not be happy with only propagating this. I need to propagate something extra. And these are potentially killer terms because I cannot expect R0 to be bounded in this norm. They will blow up, but I need to be careful. How do I actually patch up with the other smallness parameter here so that overall it gets small. Right? I need to propagate like C1 norm in space and also like C alpha norm in time. So this is just to get an explicit rate for the convergence of R. Okay, this I already mentioned that I need to stop my process. And yeah, so finally the final part is that, as I said, that I, at least for one case, I can first go up to TL. Then how do I connect? So how do I get a solution for 0T? Well, I go up to TL and from TL to T, I just connect with the appropriate weak solution of this transportation. That's very easy because we have availability of such a solution. So you go up to TL and then TL to T. But anyway, you will produce lots of non-unique solutions because up to TL you already have. So very briefly, these are kind of difficulties you will encounter. So I thank you for your attention.
Also for the online audience, there are any questions? I don't have a question. Since the title of your talk was Stochastic Perturbation.
Yeah.
There is one paper that Bandoli. They consider transport equation, but stochastic perturbation they have is stratonovich, but the coefficient is gradient of the perturbation.
Yeah, that's the way we also considered that. Yeah, like the third one.
And the third one.
It's the gradient times dV.
But they don't have the Laplacian.
Yeah, I mean that is just for the. This.
But in that case, they
Yeah.
don't have the-
Now I understand your concern because they are not in this this region.
Okay.
So they work with LPS Deterministic Approach condition, right? So that is excluded from this result. So there is no contradiction. Yeah, but thanks for bringing that. I should have mentioned this.
All right, so let's wrap up the first half of this and thank once again. So we'll be coming at 3:15, so another 16 minutes perhaps.
Please stop.